predicting equilibrium concentration. Why important? Well, you could be making potato chips, right? Or any commercial product, or just life itself. Equilibrium is where things end up, right? Just how much you're going to end up with. What's going to be left over? All those products and reactants are going to have different chemical properties. They're going to influence the environment, influence what's going on around you. Some stuff good, some stuff bad. But to be able to predict that amount that's going to exist at equilibrium, because that's where nature wants to end up. Powerful stuff. So that's really what we're after today. And I think it's important is this idea of a dynamic equilibrium. And I need some help to do this. Oh, Daisy and Jose, come on up. I need some help. Okay. This idea of a dynamic equilibrium. So we have A going to B. And there's supposed to be a double arrow on these reactions. Okay? And that's kind of what this is all about. Daisy, come over here. Here we have our A container and we have a B container. Now when we get started, we have all what? A reactant or product. When you get started, all that's there reactant, right? So I'm going to dump it in the A container. Okay. So all we have is reactant. So Daisy, she's going to be the forward reaction. Product, A going to be. Jose is going to be the reverse reaction, right? Products actually going backwards and forming reactants. That's the idea of the double arrow. Now, you hold up your beakers, right? It's like, whose reaction's going to go faster? Daisy's, right? So let's go ahead and get started. Now, the rules of the game are is both of you do it at the same time, okay? Just dump it in there. So, Jose, you have to put your beaker in the B, you have to put yours in the A, and then you dump at the same time. Yeah. So you just do it, even though you have nothing to dump. Just do it for show. Yeah. Yeah. Right, like that. Okay, go ahead. Just keep going. Keep going. Yeah. Okay. Okay, now before you dump this time, just hold it up. Are we at equilibrium? How do you know we're not? I know you're definitely right. How do you know we're not at equilibrium? How do you know you're not? You're right. Your first thought is exactly right. How do you know? The levels aren't the same. Not always true. Because just think, if you had always the same, that's kind of a good feeling. You want the levels to be the same, and then, you're at equilibrium. Well, that would mean that in every single reaction in the world, you always end up with equilibrium being half the reactants left, and you're only forming half the product you should get. Man, equilibrium concentrations are all over the place. Sometimes you get a lot of product. Sometimes you get a little product. So that's not the right answer, having the same level. Any other idea? Same concentration over, you're close. Over what? What can't be changing? Instead of the word concentration, think of amount, because you got amounts in these buckets. Constant. It can't be changing over time, right? Once you get a certain amount of product, whether it's a lot or a little bit, as long as it's not changing over time, then you're at equilibrium. And how are you going to achieve it? The amounts in these beakers are going to have to be exactly what? If they sat here and did this for 20 minutes, exactly what? The same. So keep going. See what? Yeah. Yeah. And just dip it down there and dump. You don't have to scoop. Just dump. Okay. So that's good enough, right? But that's the idea, right? And if they did this long enough, I'm not sure. I'm pretty sure there's going to be more B than A because look at this, right? Thank you very much. But That's the whole idea of dynamic, right? You're always forming product. You're always forming reactant. Backwards arrow. Okay. These beakers, one was a lot larger than the other one. What does this really represent? The size of the beaker. Because you notice how, and initially Daisy was dumping a lot. Her forward rate was huge. They had nothing to dump. His rate was essentially 0. But after a while, you notice how their rates are going to be the same because of the exact same amount they're transferring. The size of the beaker is really representative of the rate constant. This forward reaction is a huge beaker, a huge rate constant. Okay, this constant doesn't change over time. You're not filling it up, well, whatever, but you got, right, the potential, the capacity is there. Okay, so looking at that, what would you say, Kathleen, dynamic refers to with what we just did? Yeah, pulling stuff out, dumping it in the other container, right? Always forming reactants. I think that's what dynamic refers to me. Because you're at equilibrium, but hey, that doesn't mean these things stop. But if you are at equilibrium, Sochi, what would that mean? In this example, when would, if we sat here long enough, when would equilibrium be reached? Yeah, when the rate stays the same, or it's really hard to see rates though, because you know they're like it's like they're invisible. So it's not. I'm not comfortable with that answer. I'm comfortable with something I can see. Or when what stays the same over time? The volume of this stuff or the amount, right? They don't have to be the same, but just that the volume or the amount in these containers, then you're at equilibrium. And that's the exact same thing with their reaction. The amounts of reactants and products, or their concentrations, if you prefer that word, aren't changing over time. So to get us started in this predicting reactant and product amounts at equilibrium, we need to know how to write equilibrium constant expressions, and they give it a symbol Kc for an equilibrium constant. Grace, what's the little C stand for? Yeah, she's right. Concentration. Okay. Now to give you, how do you write these things? Let's pick on Juan. How do you do this, Juan? Kc is always what over what? Given some reaction, you're supposed to write a Kc expression. You remember reading this? It's always product over reactant. And you got to put them in what? They want you to put everything in brackets. What do the brackets mean again? Same thing as before. Concentration. And what units do they like for concentration? Big M, molarity. Moles over liters. Right. Now, it's not really the whole story. Products over reactants. There's really the products and reactants raised to their, big word, stoichiometric coefficient. We'll do some of these, and you'll see. Okay. Now, you never, whether it's a product or a reactant, it doesn't matter. You never include these compounds in brackets in Kc expressions. What do you never include? Anybody remember reading this? It was solids or, not gases, liquids. Solids or liquids. A prime example would be H2O. As long as it has a little L in the subscript, H2O liquid, you never include it in Kc expression. You're never going to write brackets H2O liquid in brackets. Why? Because water, liquid water, doesn't matter how much I have, whether it's a full beaker or just a drop, its concentration is always 55.4 molar. So it's a constant. So it never changes, whether the reactions be. Okay, solids or liquids? Write that. Let's see if we can write a few of these. Okay. Jessica. AC. Products over reactants. How do you write this again? Yeah, CA, the whole thing. Well, hang on. CA, right? Products over reactants. CaCl2. Yeah. Plus 2, and then in time, Cl. Now, where do you put? Technically, this is how it's supposed to be. But no one ever writes it this way. Because you have 2 chlorines, right, as a reactant. But instead of writing it chloride times chloride, every single time, they're going to write what? Where are you going to put the 2? Yeah, that's superscript. Right? So in other words, the stoichiometric coefficient is hours. You could write it out 3 times or 2 times, but it's a lot faster just to write squared or cubed. How about D? Kc is products over reactants. Oh, let's pick on D again. What would you put on top? Careful. It's got a little S on it, all right? So it's never supposed to show up. So what do you put in there instead? You can't put a 0 because then the whole thing would be 0. A 1. Okay, now Daisy, the bottom part. Ca plus 2 negative to the second, 2 squared. How about C? Go ahead and write answers for C and D, and see if it matches what I'm going to write. Or I'll ask somebody. Before you leave, you want to make sure you turn in your reading response and the review problems. That's it for today. Okay. Pick on somebody. Erica, what did you write? Yeah. All right. Everybody agree? Yeah. Products over reactants raised to their stoichiometric powers, but leaving out solids and liquids. One more, and then we can move on here. Oh, who haven't I picked on? Valerie. How did you do this last one? Okay, now where does the 2 go, though? Yeah, good. Perfect. And we can even write the gas in there if you want, but I'm lazy. Okay. Products over reactants. Good, she left out the bromine liquid. Okay. So there'll be some homework on that. Products over reactants raised their stoichiometric coefficients. Now we want to predict reactant and product amounts at equilibrium. This is the real meat of what they're trying to get at, teach you the used to doing today. And this is not in your notes. I wrote this just before class. Relax and watch. Right? You can enjoy this. We have 8 moles of A and 6 moles of B initially present. Okay. So you see the reaction, 2A plus B gives 3C. We have 8 moles of A, 6 moles of B present. But they find out, I don't know how long they had to wait, but you ended up with 6 moles of C at equilibrium. The whole question is, well, how many moles of A and B are also at equilibrium then? So what we're going to do is called an ice table. Now the I stands for initial. It's a table, so the first row is going to be initial. The second row is the C, or change. And the final row is the E, for equilibrium. So we have 3 rows. Just have to know the tricks on filling out the rows. The initial row is simply going to be, well, you just have to read the question carefully and write in the initial amount. So one, it looks like what are the initial amounts that we can put in here? For A, you'd have 8, so you just put in 8 and keep going. 6 for B. Is there anything there for C initially? It doesn't say anything, right? If it did, you just put it in. Nice thing about an ice table, it can handle anything. Okay. It's writing dashes for 0, so you can put in a 0 if you want. It's the same thing. Okay. I like dashes. Change. Now, so things are going to change. I mean, you're going to change the amounts of the reactants had better go up or down. The amounts of the reactants are going to decrease or increase. Got to decrease, right? That's what reactants do. They're going to react and form products. So, and the amount of products, therefore, are going to increase. Okay. So this is where our x's come in. Because we don't know what the answer is, so you put in an x. Pick a variable. X. Fine. That's what they like the convention. What you do is you put in, essentially you put in x, but you're not going to have, all these guys aren't going to react the same amount. There's all these ratios. Like, and look at the reaction. There's 2 moles of A for every 1 mole of B. A is going to disappear a lot faster. So what you're supposed to do is put in the stoichiometric coefficient out front. So 2 for the, 2 for the A. There's the B has a 1. Oh, but the C I better write 3. Now don't forget the pluses and minuses. We said that the reactant change is going to decrease or effectively decrease or increase the reactant. They're going to go decrease. They're going to go down. So those changes had better be negative. Products are forming. That change are negative. Positive because it's increasing. So just remember those. All right? The change row is all of our x's. The two things are stoichiometric coefficients become the coefficients in the change row, and negative for reactants, positive for products. Every single time. It never changes. Now to get at equilibrium, it makes sense that it's just, to me it makes sense, it's just the initial plus the change. And we don't know what the answer is, but it's going to be 8 minus 2x for A. I didn't make my table. I should have made it bigger. For the 6 minus x. And then for the C, everybody's going to be 0 or the dash plus 3x. I guess you could write that. Well, 3x plus 0, but all right, just 3x. Okay. So you get into your mode of doing this. You fill out the ice table. Now you check. Now the problem is just to figure out what x is. If you knew what x was, dang, here's all of your answers. You just got to know what x is, right? Does anyone see how to figure out x? Yeah. Did you hear what Eric is saying? She said that at equilibrium there's 6 moles of C. So that means this number right here, that's got to be 6. Then she even told us the equation. 6 equals 3x. That's how you get your x. They're going to tell you a reactant or a product at equilibrium. So you fill out the ice table first, right? Fill it out completely, all x's and things. And then you go back to the question to see which one you can solve for. In this case, it's C. So my x is going to be 2. Now I know everything. At equilibrium, I'm going to have, right, let's see, 8 minus 2x, which is what? 8 minus 4. We're going to have 4 moles of A. Right. I'm going to have 6 minus x, or 6 minus 2 is 4. Huh, I end up with the same, huh? 4 moles of B. Just so happens they're the same, they don't have to be. And then they want to know the equilibrium composition, so you really should give them all. How many moles of C do I have at equilibrium? 6. Don't write 2. Because they told us there's 6. And that's 6 moles of C. So this would be a complete answer. Right? You give all the moles of everything at equilibrium. And remember, the answers are all in your equilibrium row. 8 minus 2x, 6 minus x, and 3x. Okay. And just plug in what x is, and you'll have them all. Okay. Let's try another one of these. Okay. What is the equilibrium composition reaction that's initially present were 4 moles of calcium, 6 moles of phosphate, and then at equilibrium 0.5 moles of calcium phosphate? Okay. Grace. I'm going to get you started here. Let's do the I row first. What would you put in for that? 4 for this guy. 6 for the phosphate. Now, if it's a 1, they got to say that there's 1 mole initially there. Did they? No, just 0 or a dash. Right? In fact, one thing that I forgot to do, and it really helps, is what if one of those reactants or products was a solid or a liquid? What would you do? Remember, they have no influence. Their amount stays the same. So if you ever see a solid or a liquid, let's pretend this guy, just pretend he was a liquid. Then you put dashes all the way down. Doesn't it play a role? That's why I like the dashes, because instead of zeros, because they cover both cases. If you see a solid or a liquid, you just put dashes all the way down. But he's not a solid or a liquid. Okay? So we have to play with them. And there's nothing there initially, so I put a dash. Okay. So Kathleen, what should we put in the change row? Good. Minus 3x. Minus 2x. Oh, not yet, not yet. So don't mess with the equal. Done filling out the ice table. Otherwise, it gets confusing. So what's the change for the calcium phosphate? Anybody see it? You just put in a x. And it should be positive or negative? Positive. Okay. So that's my suggestion. Don't mess with that equilibrium guy. Right? The equilibrium amount until you're totally done filling out the ice table. Equilibrium row. Sochi, what are you going to put in for the equilibrium row? She's just adding them up. 4 minus 3x, 6 minus 2x, and x. Okay. Daisy, where are all of our answers? Yeah, the last one. Here they are. This is the only one we're supposed to be looking at. Okay. So what's the equilibrium composition? You could give 4 minus 3x for calcium, 6 minus phosphate, but you're going to get half your point, so you got to figure out what x is. Valerie, how do you figure out what X is? Yeah. In fact, we should set up the equation. She's right, it's 0.5 moles. But it's whatever this thing is, you set it equal to 0.5. It could be 2x, 3x, 4x, who knows? But he has to be 0.5. Because it's the amount of the calcium phosphate, whatever we wrote right here, that's what goes, that's the equilibrium amount. Okay? Well, then we can do the rest. 3.5 times 3 is what, 1.5? 2.5? 2.5 moles of calcium. We have 6 minus 2x. Let's see, 1.5 times 2 is 3, right? That should be 3 moles. Phosphate. And then how many moles of the calcium phosphate? Yeah, 0.5. See, I can't do things in my head. I shouldn't even have tried. What's wrong with these guys? I'm erasing them all because I don't trust them. 2.5? This guy's 5. That is so sad, isn't it? But at least that's one thing I can relate to you guys on, because I bet you're the same situation as me. You're the calculator generation. Okay. Make sense? So you see the reaction. They want to know equilibrium composition. You make your ice table. Okay. Try this one. Try this one on your own. See if you can get it to work. What is the equilibrium composition for the below reaction if initially present were 1.5 moles of calcium, 2.75 moles of hydroxide? They're mixed in equilibrium, you have 0.25 moles of calcium hydroxide. It's the equilibrium composition. Not sure where to start? Glad to help you. Fill out the ice table completely before messing with that equilibrium amount of 0.25. Fill out the ice table completely. Otherwise, it's too easy to mess stuff up. Sochi, what did you get for calcium? We'll see if other folks get the same thing. 1.25 moles of calcium. 2 point what? Moles of hydroxide. And the other guy's got to be 0.25. Yeah, Juan got it. That's got to be right. Juan got that too. 2 folks get it. Odds are. Did you get it to work? What do you put x? X has to be this divided by 2. So x is going to be what? 0.125 or something. What's 0.25 over 2? Yeah, because this has to equal 2. Because this number should be 2x. Don't put numbers in until you get this done. So nothing plus 2x is 2x. That should be a 2x. Erase that. That should be a 2x. No. Put in 2x. Otherwise that's what I'm saying. Otherwise you get screwed up. Don't put the equilibrium amounts in yet. So put in 2x there, because it's 0 plus 2x. Now you circle this thing. That has to equal 0.25. So 2x equals 0.25. So you have to divide 0.25 by 2 to get your x. 0.125. So in this question, you should be getting 0.125 for your x when you do all this work. If you're getting 0.125 for your x, you're on the right track. Okay. Let's see. I'm going to come back to this 29. I want to skip down to this one, 44, because it's a change different. A 4-liter vessel containing 0.0148 moles of the phosphorus trichloride, PCl3, 0.0126 moles of phosphorus pentachloride, PCl5, and 0.087 moles of chlorine, that's the Cl2, in an equilibrium mixture. Calculate the value of Kc for the reaction. Okay. Let's pick on somebody. Pick on Jose. You never make eye contact. Is this an ice problem? It's not. He's right. The only purpose, to me, the only reason to do ice is to get that, right? Because remember we said our answers, they're always in this E row. That's the only purpose of doing ice. Well, they told us it. I think he's totally right. All right? Didn't they tell us? Where is it? In an equilibrium mixture. We're done. There's no point to do ice. I mean, they could have. They could have made this a really nice question. But they didn't. I mean, nice in my sense. All they want to know is what Kc is. So, to me, it's the same logic as we did before. Is you pick the right equation and plug in what you know. But in this case, you have to write your own equation because it's Kc. And Kc is going to be different depending on the reaction. So Kc, Becca, how are you going to write the Kc expression for that reaction? Remember, it was what over what in brackets? The PCl5, the product in brackets divided by the reactant in brackets. And notice there's no, all the stoichiometric coefficients are 1, so you don't have to worry about any of that. And there's no solids or liquids, so you don't have to worry about any of that. Just copy them all down. Now, do you see the problem? I am really urged to type in for phosphorus trichloride. I really want to plug in this number, right? Why can't I do that? There's something wrong with that. I can't just put in 0.0148. It's not molarity. Grace caught it. Those brackets mean molarity. You have to plug in the molarity of PCl5. the molarity of PCl3 and the molarity of the chlorine. You have to, because that's what the brackets mean. Okay, so we got to get those. And I want to do that off somewhere. How do we get molarity? It was what over what? Does anyone remember? It was moles over liters. So that means to get the concentration, the molarity of PCl5, divide what by what? Each one of those by 4, exactly. 0.0148 moles of the PCl5 divided by the volume in liters to 4 liters. Do the same for each one of these guys. And that's what you plug in to the Kc expression. See if you can get it to work. Yeah, G. Yeah, phosphorus. Oh, I for the wrong one, didn't I? That's not 0.0148. Thank you for noticing that. That's for this guy. PCl5, she is so right. That's got to be 0.0126. Right? Thank you. All right. So you gotta know how to use your calculator to figure this out. All right. I think if you do it right, you can get around. What'd you get, Jose? 39. Yeah, I think that's about right. Somewhere around 40. Depends on how many digits you're carrying on your calculator. You should get around 40 if you're doing this right. So if you got it, go on. I don't know. Let's do that one. That should be a quick one. Do 55. Make sure you can get that 40 in your calculator, though. The last class was having a lot of trouble doing that. on 55, what? Oh, let's just write it out, right? There's a couple tricks in there. And 55, Jessica, what did you have on the top? Yeah, all she has is CO2 in brackets. On the bottom, oh, Erica, what did you put on the bottom? The SO2, all that's in brackets. Yeah. Exactly. Does anyone know? What's the 1/2 better known as? Like usually when we say 2, we say squared, 3 cubed. What's the 1/2? It's actually the square root. Yeah. Okay. 1/3 is the cube root. What else do we have here? Let's try this one. You can do this, man. I think you're totally ready. That 2x has to be the 0.0311, right? These are your answers. So the 2x has to be, what's the equivalent? Yeah, so 2x has to equal this. So just solve, you gotta solve for x. You forgot your 2. 2x equals this. Then divide by 2 to get your x. Because this whole thing, whatever you end up with here, that's got to be the equilibrium amount. 0.0311. Oh, you put it all on. Yeah, it's good. The initial NO is 0.0524. Initial BR2 is 0.0262. So how do you do this? So you pretty much just write the reaction verbatim, then you write ice under it. And you go searching for that, whatever there initially. And then write the change row, negative for reactants, positive for product. Don't forget about the stoichiometric coefficient. Yeah, so that 2x has to, there you go. Exactly. That's how you get your x. Did you get answers? Juan, what did you get for your question? Jose, is that what you got for your x? All right. And then we need, Jose, what did you get for moles of NO? Your final answer. Or not Jose, Juan, what did you get? 0.0213 moles of NO. Is that what you got? Yeah. Now keep going. What did you get for bromine? 0.01. NOBR, we said was 0.311. So a couple people got this. I bet you those are the final answers. So I'll be glad to help you on this stuff. Don't let it slide. Before you leave, turn in your reading response and the review problem, because that's the quiz for today. Lab Thursdays, is that 8:30? We'll have lab this afternoon. Yeah, 1:30.